So today we have kind of a two-part webinar. In the first part, I'm going to talk about what I like to call black box performance analysis, which you can do simply by capturing some TCP traffic. And this is interesting and important. You don't have to capture all of the traffic. You can only capture just the fact that packets are arriving and departing. You don't even have to know what the contents of the packets are. And you can learn a lot about a system in a very cheap and easy way. It's a very effective way to get a head start on learning what's going on inside of the system without spending a lot of time and without needing a lot of access to the system. And in the second part of this webinar, I'll show you how you can take that data, which let me continue with the first part here, actually. In the first part, I'm going to show a variety of ways that you can do performance analysis with that data. In the second part, I'll extend the use of that data further into scalability and performance analysis. Finally, I'll try and wrap it all up and show you where it's useful in the real world. So just to kind of motivate the discussion a little bit, you start off with a little bit of perspective. As a consultant, I'm often called into systems that I don't know very much about. I'm asked to solve problems on systems that I've never worked on. And sometimes in an emergency, but even if it's not an emergency, it's often very desirable to have some idea of what's going on in the system or how much time and effort and money we should really invest into the project. And to do that very cheaply and quickly at the beginning of the project, as I said before, without requiring a lot of things that are difficult. So although I do this on systems that I'm unfamiliar with, you can also do it with your own systems. And this is something that anybody can do pretty easily. Doesn't require much knowledge, and it doesn't require a lot of software to set up or anything like that. You can just kind of get started and see if you can learn something about your system that you might not have noticed before. In fact, there are often a lot of what look like really obvious things going on in a system in hindsight that the kind of techniques that I'll show you can bring out very clearly, and then you can dig into those phenomena. They may be problems, they may just be kind of the way the system behaves. In any case, it's a great way to get started and learn more about your systems at levels that you can't really observe just by kind of watching the queries that are executing in the show process. But sort of the typical kinds of things. You will be able to find things out at the sub-second granularity, the kind of stuff that you don't see in any graphing and plotting system. So I like to use TCP traffic for this. And most of the time, or much of the time, people will set up MySQL on one server and an application on another server, and they'll communicate through the network. So TCP/IP is the protocol that's used there. It's the carrier for the MySQL client server protocol. And it's a great way to investigate what's going on in your system. What's nice about it is that pretty much any protocol, such as the MySQL client server protocol, anything that has sort of a call and response semantics can be analyzed with the techniques that I'll show you today. So, for example, you could easily apply this to PostgreSQL, to Memcached, Redis, MongoDB, many other database servers, many other caching servers. In fact, you can do this with web services and with HTTP traffic and all kinds of things. Lots and lots of different systems are amenable to the types of analysis I'll show you today. And what you get, or sort of the most basic thing that you can get, is what I like to call the fundamental metrics of performance. And no one else defines these as the fundamental metrics. This is just kind of the most basic things that I've been able to break things down in my practice and experience. And that is the fact that some request arrives at a system and what time that happens. And then when the completion of this, when the message is sent back to the system that made the request, we call that a completion, and we can observe the timestamp of that as well. So now we know arrivals and completions, which represent the beginning and end of queries in the case of MySQL, but in many other kinds of systems, it would be some other sort of request. So basically, you have some application that sends a request, and it spends a little bit of time on the server being processed, and then the response comes back, and you call that the end of the query or the end of the request. And just those two timestamps and the ability to correlate them together allows us to do a lot of interesting and very powerful things. So from that, we can get a bunch of metrics about the system. The first that I'm listing here is the observation interval. The observation interval is defined by when I start looking at the system and capturing some traffic and when I stop. So if I capture traffic for 5 minutes, my observation interval is 5 minutes. And within that observation interval, I can easily derive the queries per second. I think it's fairly obvious how we get that. And the busy time, I call this the busy time. Different people have different names for it. This is the time, the portion of time during which there was at least one thing executing on the server. And the total execution time, which would be the completion time minus the arrival time of all of the requests that we saw arrive and depart during the observation interval. So an example here might be that we capture traffic for 5 minutes, and we have, let's say, 10,000 queries per second, and we have the busy time. Most of the time that we watched the server, something was happening on it. So let's say that during this 5-minute window, we have 4 minutes and 45 seconds of busy time, and the total execution time might actually be greater than 5 minutes. If there was concurrency, multiple concurrency on the server, let's say that there were on average several queries executing at any given time, we might have 10 or 15 minutes of total execution time in our 5-minute observation window. So from that, we can use Little's Law, which I'll show you in a later application as well, and we can further derive some more metrics. The throughput is fairly easy. Throughput is actually equivalent to queries per second. We just simply count the number of arrivals or departures, arrivals or completions during the observation window and divide it by the length of the observation window, and we get throughput. Little's Law is predicated on the system being a stable long-term average. So in a stable system, you have as many completions as you have arrivals. You don't have things backing up infinitely. And during any reasonable period of time, the properties of Little's Law hold for finite systems as well. A stable long-term average actually looks very much like what we get when we have, let's say, that 5-minute observation window. If we have 10,000 very short queries per second for a 5-minute window of time, it's so close to a long-term stable average as to be completely indistinguishable. So that's why we can count either the arrivals or the completions, because the likelihood that we get many more arrivals than completions around the boundaries of that observation window is very small. I hope that makes sense. Concurrency. We can figure out the average concurrency during the observation window by watching how many queries are arriving but not yet departed at any point in time, and I'll show you graphically later how to do that. We can get the average response time of queries, and we can get the utilization. And utilization is really pretty much equivalent to concurrency in this sense. So we can get a lot out of just arrival timestamps and completion timestamps. There's a particular way that I do this, and I've built a particular set of tools to enable and script this and make it more efficient. And I just use standard TCP-dump, which is available on everything except Windows systems, and on Windows systems you can even use WinDump. I'll explain the TCP-dump command line arguments here. Now there are variations on different systems. For example, on Solaris there's Snoop, and on FreeBSD, TCP-dump might have slightly different command line arguments and so forth. What I'm showing you here is from Linux, but it's pretty much equivalent to anything you can run on most Unix-like systems. The first option here is TCP-dump-S384. That means that I'm going to capture the first 384 bytes of each TCP/IP packet that flows through the system I'm watching. And 384 is not a random number. That's actually, if you know your TCP/IP protocol, it is the number of bytes in the TCP headers and the IP headers, packet headers. So what this means is that I'm actually looking only at the packet headers, and I'm throwing away the payload. So there's going to be some packet payload beyond this that will contain protocol information that MySQL understands, including, for example, the text of the queries that are flowing in and out of the system, contents of the rows that are returned in response to the query, those kinds of things. But we throw all that away, and we're only capturing the first 384 bytes. And there are several reasons to do that. One is, for the analysis that I'm doing here, I don't need any more than that. All I need is this timestamp. And the packet headers, though, contain the IP address and port of the origin and destination of the packet, and I need that to determine who the packet is from and to. Okay, so I'm just capturing the 384 bytes there of the headers just for that reason. The -I, any means to listen on any network interface on the server. -NNQ just abbreviates the output format a little bit. 4T options format the timestamps. And then we have this complicated expression on the second and third lines on the screen. TCP port 3306 restricts us to capturing data that is intended for port 3306, which is where MySQL listens by default. And then we have a really funny, awkward-looking expression after that with square brackets and all kinds of things. That is pulled directly out of the tcpdump man page. And basically what that means is ignore any of the packets that are at a lower level than the client-server protocol that MySQL understands. It means to throw away things like the TCP connection, the three-way handshake when a connection is established, and acknowledgement packets that let TCP know that everything was transmitted and received okay, all of those kinds of things. We throw that away because those don't actually correspond to query activity. They correspond to activity on the network that is at a lower level than the queries and responses that we want to be tracking. And then finally, I redirect the output into a file, just calling it tcpfile.txt here. Here's the first 3 lines of that file for just sort of a sample. Now, in the first line here, it begins with a date and timestamp. So the first line here was a packet. There's 1 line per packet. It was a packet that arrived on May 5th at 10 o'clock, 10:47:17 in the morning, and then some number of microseconds, 810932 microseconds. So there is a microsecond level timestamp here, and that's created by the -pt-tcp option that I gave to tcpdump above. And then the letters IP, and then the origin and destination IP address and port number of this packet. So this packet came from 10.220.146.79, port 35805, and it was headed for the MySQL port 3306 on the IP address 10.119.42.41. The final couple of words on that line, TCP83, actually indicates the rest of the payload. There was a further 83 bytes of payload in this packet, but we've truncated that and only captured the headers. But that's how much remains in the packet. The second line shows the response back from port 3306 on that .41 IP address. So that's MySQL responding back, and it's sending a packet back to 10.220.146.79, port 35805. So this is the second line here is a packet that's sent in response to the first line. The combination of those 2 lines represents a single, what I'll call a request or a query, the arrival and the departure of a single request on the server. And then the third line is just the beginning of some other process on a different server sending another query into the server, and so on and so forth. And on a busy server, of course, you'll get thousands of tens of thousands of lines like this. And I've just shown here that the first 3 for illustration purposes. So before I dig into the data, I want to characterize the data just a little bit. There's a whole series of graphs that I'm going to show you here, and they're from a single 17-second long sample of TCP traffic from an e-commerce website. It's a popular shopping network, and it's running in the Amazon EC2 cloud, and this is a MySQL server. So this is real data that we're about to see. So we take that TCP file.txt where I saved the output of tcpdump, And we run the pt-tcp-model tool against it and save the output again into request.txt. Now, pt-tcp-model is a tool that I wrote that's included as part of Percona Toolkit. This is open source free software. It's available at percona.com/software. And there's a whole variety of administration tools there. This is just one that's particularly focused on the type of modeling and analysis that I'm going to show you here today. And I've shown you the first few lines from the resulting request.txt file. Each of these lines, instead of a pair of lines constituting a request, what I've done is I've taken that tcpdump output and I've matched up the arrival and the completion and put them onto a single line here. So line 0, all the way on the left there, we have an integer that represents the order in which these requests arrived at the server, and that'll be important for later. So request 0 started at some start timestamp and ended at an end timestamp, which was 89 microseconds later. The third column, sorry, that's the fourth column there that I've put a header called elapsed, is the subtraction of the ending and the starting timestamp. It just makes some of the further work that I'm going to do a little bit easier to have so that I don't have to do a subtraction in some of the tools that I use to do some plotting and charting. And then finally, we have the host and port from which this request originated. And I don't refer to that again. I really put that there so that I could, if I wanted to reference back to the original TCP dump data, I could do so pretty easily. So we've got here looks like five packets or 5 requests that arrived and completed on the server with varying response times from 89 microseconds to 245, or actually one's 302 microseconds long. So these are really queries that are running in MySQL. And I have the start and end timestamps. Those are the same thing as the arrival and completion timestamps and the elapsed time. And from here, we can take off in a number of very interesting directions. We can do all kinds of stuff to this data. The first thing that I usually like to do is plot it as a time series from left to right with response times on the vertical axis. So from 0 to 0.3 here, we have query response times. That's the fourth column in my data. I generated this plot with a tool, free software plotting and analysis tool called GNUplot. It's a command line tool. It's very easy to use. I encourage, if you're going to be getting into this kind of stuff, encourage everyone to get familiar with a good command line tool. R, the statistical analysis package, is another good tool for this. Spreadsheets don't tend to work so well. They're very cumbersome with large amounts of data. But the data that I've output in this columnar format is very easy to work with tools like R and GNUplot. So it's a one-liner to generate this graph. I simply say plot, give it the name of the file, and then say using for. And that means using the fourth column in that data, which was the response times, the subtraction between the end and the start timestamp. And I get this plot. It takes about 10 seconds. It took a few more seconds to add the labels onto the plot, but no more than that, really. It's very handy. So the reason that I like to plot this data first is because I have a very sophisticated pattern matching and pattern recognition computer embedded in my head. Actually, a few of them. There's my eyes, and then there's my brain. And I can look at this, and I can see that there's an interesting pattern here. And I'm able to do that visually much more quickly than I can do any other way. I cannot look at this data in some kind of textual format and see the pattern in the data. It would be like trying to watch the matrix and see things scrolling by. Human brains are just not very good at doing that, but we are good at looking at a chart like this and seeing patterns. And I think there's a very strong pattern here immediately. It's crystal clear to me when I look at this. There are these interesting, what I'll call spikes of long response times. So here I'm going to draw an arrow right next to one of them. So apparently there was a query about halfway through the 17-second sample of data that took 0.3 of a second to complete. And then just below it vertically, there were some others that took 0.2 of a second, 1/10 of a second, and so forth and so on. And this is interesting because we have some real outliers here. We can see this visually pretty clearly. Most of the queries run in under 200 microseconds here, and they're clustered into a solid red bar along the bottom of this graph. But we do have these funny outliers. Looks like just a handful of them. And they're repeated on a fairly regular basis. Looks like maybe every second or so we've got some spike of long queries running on the system, which is interesting and unusual. So immediately I've been able to answer my initial question was, is there anything interesting to look on this system? You know, does this system merit digging in deeper? And just by looking at this spike of long queries, I can say, yeah, there's something funny that we ought to investigate here, because this looks like a system that's running somewhat inconsistently, and I don't like systems that run inconsistently. I want everything to be consistent, predictable, and uniform. The other interesting thing here is that these spikes are actually slanted a little bit, and that's not an optical illusion. They really are angled from left to right. And you might ask, why is that? Well, the reason is that I've actually plotted these in order of the completion timestamp. Just by default, the tool that I've used, the pt-tcp-model tool that I've used here, outputs each request as it sees the completion come through. So by default, it outputs every request in completion order. And when you chart things in completion order, a lot of interesting things come out of the data. What it really means here in this case is that we had a 3/10 of a second query that completed, and then it looks like a series of queries were able to complete very shortly after that. So this is interesting and meaningful. It's not an accident that this sort of diagonal pattern comes out of the completion timestamp. So what's really happening here is that each query completes when the previous one releases some resource that it's holding. So we have some long 3/10 of a second query, which is quite an outlier from 200 microseconds, and it's holding a lock or something like that. It makes other queries queue so that they have to wait for the resource before they can go ahead and complete. And that's why they complete one after another. Looking at completion timestamps is therefore a very sensitive tool for detecting when things are stalling and blocking on each other, because completions tend to be affected. Arrivals come in randomly into the system. Most systems, this one included, behave fairly randomly. The arrivals arrive in an uncorrelated fashion. There's a particular mathematical distribution that describes it, but it basically means that they arrive randomly. But we're seeing some non-randomness in the departures and the completions, and that's where those spikes come out. In this case, it's actually caused by select for update queries. A select for update query will lock the row, and then other queries that come in will try and do a select for update, and they'll have to block and wait until the first query releases that lock and commits the transaction. And that's why we get these strange, long-running 3-second queries, probably because there are 3-second transactions. The application is doing some sync time before it actually commits its transaction and frees up the locks that the other queries need to do their work. So that's why we see those spikes. It's not that the queries themselves took a long time to complete. It's that they spent a long time waiting for locks. So this is kind of stall detection algorithm number 1. So I said that completions are a great way to pull the signal out of the noise. Maybe if I just plot the number of completions over time versus the number of arrivals, I can see some different patterns. And I'm just, again, these are all one-liners at the command line with the new plot tool. So first I'll plot the arrivals. And here I'm actually doing something a little different. This is not time series. What I've done is crunched these into time slices 5 milliseconds long. And I've counted the number of arrivals in each 5 millisecond time slice. So you can see that there are some slices of time in which we have as many as, 33 arrivals at the server. Most of the time we're around 5 or 10 or 20 arrivals per 5 milliseconds, but it does go higher than that. And I like to look at this and just visually, is there a pattern here? Is there something interesting going on here? And I would give you a caution here. Although humans are very good at seeing patterns in things, we're also very good at seeing patterns where none exist. So when I look at this, even though it looks like there might be some kind of patterns, I'm going to conclude that there's no really strong pattern, because I've seen many times when I've dug into things, and I found that the patterns that appeared to be there were just random or just a figment of my imagination, sort of like looking at the clouds and seeing shapes in the clouds. So those are the arrivals for 5 milliseconds, and I've also plotted the completions for 5 milliseconds. And I'll just flip back and forth between these for a second so you can kind of compare them visually. And I don't see a strong pattern here in the completions either. I would say there are some points where we have kind of what look like outlier points. Maybe about a third of the way from the left, it looks like we have sort of a spike of completions that are, it looks like for a few periods of time we had a very high number of completions relative to each other. But that might, again, just be my eyes fooling me. So I'm going to conclude that there's nothing to conclude from these two graphs. Now, I know that there's something going on with the completions of this server, so I'm probably just doing it wrong, probably graphing this stuff wrong. I probably just need to try a different technique that'll pull out the signal out of the noise again. So the first thing that I'm going to try and do is I'm going to aggregate in much larger slices of time. Instead of 5 milliseconds at a time, I'm going to do 200 milliseconds at a time. That's 2/10 of a second. That's a pretty large slice of time relative to what we expect queries to actually run for on the system. If you remember earlier, we saw that the longest running query was only 3/10 of a second, and most of them are in the hundreds of microseconds, actually, very much smaller even than 1 millisecond. So I'll go ahead and carve it up into 2/10 of a second and see if there is really a problem. And that's what I've done here, and I've changed from plotting points to plotting lines just so that it's a little easier to look at. And I would say it looks like maybe there's some substantiation to my earlier guess that there was a spike of completions about a third of the way or a quarter of the way in from the left. Looks like there might be. I'm not sure, though, if that's really significant, because when you look at this line, I mean, it kind of looks like a random line. It goes up, it goes down, and that might not be very statistically meaningful. But what if I compare this to the completions? So this is the arrivals. Here's the completions. And I don't know how quickly your screens are refreshing, but if I flip back and forth between this a little bit, maybe you can see there's a little bit of wiggle in the graph, but they mostly look pretty much the same. And it's very difficult. I tried a number of different things, like plotting them on top of each other and those kinds of things. And generally, the graphs, the lines look pretty much the same, and it's hard to tell whether there's anything meaningful here. There's a simple technique, though, that can pull out the difference between these, and that's just to subtract one from the other. So if I subtract the completions minus the arrivals, the spikes come out very, very clearly. And this shows us the difference between variations in the traffic that's arriving at the system and variations in the traffic, the way the traffic is actually being handled inside of the database. So what's interesting to note here is that, let me flip to the previous slide again. We have some spikes here, but are those spikes because queries are stalling, or are the spikes because the application sent more queries at that time? It's a little hard to tell. In fact, it's basically impossible to tell. You don't really know unless you measure the inbound and outbound traffic on the server. So when we subtract the arrivals from the completions, that's what we get here. We get this kind of EKG monitor. Looks like somebody with a pretty bad heart rhythm that needs to go see a doctor quickly. And I don't like to see spikes like this. A spike where there's a very low, first, if you'll notice, the spike dips down and then it goes very high up. That means that there's a period of time at which there are very few completions relative to the arrival. And then there's another period of time at which all of the queries that apparently backed up there go ahead and flush through the system and they complete. And this, to me, it's a very telltale sign of something backing up inside of the server and causing some blocking. So this is a very sensitive algorithm for pulling out spikes of locking or stalling inside of the server. And again, it takes much less time than I've spent on this webinar to find this out. You go grab 30 seconds worth of data, you plot it, a couple minutes later you're done, and you see this and you know that there's something interesting to look at on the server. So this is my second pile-up detection algorithm. Now, one thing, when I initially did this on this particular set of data, I tried a bunch of different granularities. I started at 5 milliseconds, and I basically backed all the way out to about a second, and then I zoomed back to 0.2 of a second, because that's where the spikes really started to show up. Now, on any computer system, a computer is really a network of servers or resources that get some work done, and then connections between them, and there are typically queues in front of those resources. So it's a network of queuing systems, if you're familiar with queuing theory. And the nature of such systems is that they have little spikes and stalls and pile-ups, and that happens all the way down to the very lowest levels of the hardware. It's just the way things work. So if you zoom in far enough, I can guarantee you, you will find spiky behavior in your system. The question is, it's not whether, but it's at what level you see that behavior. And if you see the level at 0.2 of a second granularity, and that's not an acceptable granularity for you, then you've got a problem that you might want to look into. If you see this behavior at 5 microseconds, I would say, well, of course you're going to see it at 5 microseconds. I mean, computers don't get a whole lot of work done in 5 microseconds, especially if any kind of memory traffic is required or anything like that. So it's just a matter of zooming in and out on the granularity until you find where the spikes are, and then you ask yourself, well, is that really a problem or not? The key thing to notice here is that at 0.2 of a second, this e-commerce website's customers are not going to be complaining. We see evidence of a series of problems that is beginning to occur, but it's not yet noticeable to humans, and in fact is not yet noticeable to most ways that humans might analyze the system using tools. So this is a way to discover latent problems that are going to get worse over time, and you can get a real early warning here. This is a very sensitive technique. There's another technique that I like to use, which is the index of dispersion, also called the variance to mean ratio. And this is a statistical metric that's related to the standard deviation and the variance and lots of those other statistical metrics. It has some advantages. For example, it's normalized, as I said here, relative to the average response time. And that's an advantage over some of these other metrics like the standard deviation. If you look at the standard deviation of response time on one system and then another, you don't really know whether it's good or bad because those systems might actually have very different workloads. But by normalizing them down to, it's not exactly a dimensionless number, but the dimensions turn out not to really matter, you get something that you can compare pretty well across systems that may even be behaving quite differently. So here's the index of dispersion of response time. Most of the time, it's rock steady down there in the very, very small fractions of a number, and then we get some spikes. And what's in those spikes would be a good question. That's another thing to dig into. So yet another way that we found something interesting to investigate on this system with some spikes up to 10. And I can't tell you whether 10 is good or bad. I can just say that 10 is a lot higher than the typical performance. When there's a spike in the index of dispersion, it means that something is running very irregularly within that time window. And variable performance is bad. I want consistent, predictable performance. Variable performance also means that things are optimizable because it typically means that something is taking some very different paths, execution path within the system, whether it's a cache miss or some locking or what have you. There's something in there that we might be able to analyze, figure out where the inconsistency is coming from, and make it much more consistent. So altogether now, our spikes of completions are spikes of completions minus arrivals, and then these strange spikes of index of dispersion in this data. So this concludes the portion one of our webinar where I've, without really knowing anything about the system, I've demonstrated that I can figure out at a very fine granularity that there are things that we need to look into. And what those exactly are, we'll spend some more time and effort doing that. But at least I've cheaply and quickly figured out how to kind of frame the scope of this project. This works in the real world. This is one of our customers. And he analyzed some inbound traffic on port 80 of his load balancer. Now this is before it gets to the application servers. It's before it gets to the database. This is all upstream from the database. And he found extremely bad, the aggregation interval here is 1 second. Extremely bad spikes of basically 0 throughput at the TCP level. And took this graph over to the network provider and said, you need to fix this. Something is going wrong with the network. And indeed, they did figure out what was going wrong with the network, which doesn't need to concern us here. But this was a pretty easy way to get started here. And otherwise, you know, there could be hundreds and hundreds and hundreds of metrics that you might spend your time looking through trying to figure out what's going on the system. So from this, I want to move on to scalability and performance analysis that I can do on the very same type of data. Now, as before, I was using only one 17-second long sample of data. I gathered several, I think it was 8 samples of data from that server, and I'm going to use the combination of those 8 in the graphs that follow. Before I start talking about scalability and performance, I want to define what I mean by scalability. Now, there could be many different definitions of scalability. I want to use one particular one, which comes from Dr. Neil Gunther, so that we can agree and talk precisely about scalability, so that it's not a vague notion that we're kind of tossing around and maybe talking about different things without realizing it. Dr. Gunther wrote and said many times, scalability is a function, but I didn't really appreciate it until I understood that he meant it's an equation. And in fact, it's a mathematical equation. It's not a terribly complicated one, or at least the model that I'm going to use that he developed is not terribly complicated. The x-axis is the concurrency and y-axis is throughput. So let me show you what I mean there. Let's suppose that we have one user on the system and we get some level of throughput. That's queries per second. It doesn't matter what that is. It just matters that we have one and we know what the throughput that comes out of that is. Now, a linearly scalable system, if I increase the number of users on that system, I'm going to get equal return on investment, or equal bang for the buck is another way that I've heard it said. If I double the number of users doing some work on the system, I will double the number of queries per second that get executed on that system. In other words, when I ask the system to do twice as much work, it actually does twice as much work. And if I ask for 3 times as much work, we get 3 times as much, and so forth and so on. This is also a linearly scalable system. It happens to be a lower slope of that line. What's important is that both of these lines go right back through the origin. If you see, for example, at a trade show, somebody says, our system scales linearly, and they have some plots on a benchmark, do just a little bit of math and find the slope of the line between the points and make sure that it actually goes through 0. Most systems don't scale linearly. And the important thing to know here is not that the points are lined up in a straight line if there were 3 or more of them, but that they're lined up with the origin. So here's a typical system, right? We don't get exactly linear scalability out of the system. If we drew a line through those points, it would not go through the origin. And this is actually very, very common. I mean, most systems behave this way. So why does this happen? What causes systems not to scale perfectly linearly, which the vast majority of systems don't do? It turns out that there are really 2 effects at work here, or 2 effects that are sensible to talk about and easy to model. The first factor is that not everything can happen in parallel. There's always some portion of the work that has to be serialized, or almost always some portion of the work that has to be serialized. So for example, if 5% of my work has to be done in serial, then I'm never going to be able to reduce the total time it takes to complete that task below that serial portion. No matter how fast I make the parallel portion, I've still got to wait for that serialized portion to complete at its own pace. And here's an expression of Amdahl's law, which models this very well. And don't get scared by the math. This doesn't have to be overly mathematical. What this says on the left-hand side of the equal sign is that the capacity at concurrency of n is equal to n over 1 plus some sigma times n minus 1. And sigma turns out to be the serial portion of the work. So if 5% of my work has to be done serial and can't be parallelized, sigma would be 0.05. It's really that simple. And the portion of the work, as n grows, the serial portion begins to have, if you imagine this going out to infinity, this ends up being an asymptotically rising function. So it's always increasing, but it gets slower and slower as it basically approaches the serialized portion of the work. Factor number 2 is what I call coherency. Some people call it contention. And this is when multiple things are working in a system and they have to coordinate with each other. And this can happen at multiple levels in the system. For example, one of the things might be on a multiple processor system. A processor has to wait for a cache line to become valid when the memory is marked dirty somewhere else by some other processor. And when we add this into Amdahl's law, just all I've done is I've added another term in the denominator here. We get Dr. Gunther's universal scalability law. So this models a system where there's some serial portion, and then there's some portion of work that requires crosstalk or coordination among the workers on the system. And the part that I've highlighted in the red box there actually increases quadratically as the number of processes on the system increases. N times n minus 1 is essentially equivalent to n squared. So that grows, at some point, it grows even more quickly than the throughput of the system of a linearly scalable system would grow. So we have two coefficients of the two terms in the denominator here, sigma and kappa. Sigma is the serial portion, kappa is the portion that requires some coordination among the workers. And when we plot those out, the black line is linear scalability. Amdahl's law is the red line, and as you can see, it approaches eventually some asymptote. It basically hits a ceiling. And then the blue line is Dr. Gunther's universal scalability law, which actually has a peak, and then it starts to level off and decline after that. And this matches what real systems do. Most real systems reach a point where if you ask them to do more work, they will get less work done. And that's just the way things work. You can see this in lots and lots of queuing systems in real life. Consider the freeway. You get too many cars on it, and everything slows to basically a standstill. If you take some cars off of it, the total throughput of that highway actually increases. So this is a useful and simple enough model. Again, the equation there, it's not very complicated. It might look a little scary, but trust me, it's really not a complicated equation. You can just work this by hand even. And this is a useful model that describes the blue line that sort of matches what real-life systems do. This is the best model that I have ever come across. There are lots and lots of other models, but they're either insanely complicated mathematically, or they do strange things like they go negative. We know that we can never get negative work done from a system, right? So this one seems to match the real-world behavior of systems pretty well. So we can use this model, this equation, as a scalability forecasting technique. We can measure the throughput and concurrency, which are the inputs that we need to it, and perform a regression. And if you're familiar with spreadsheets, you can do a linear regression or even a quadratic regression and fit a curve to a series of points. Here we're fitting a more complicated curve to a series of points, but that's basically the same thing that we're doing. It's just a regression. And the result of the regression is that we'll get the sigma and kappa coefficients out that we need to plug into the bottom of this equation. And then with some experience and intuition and judgment and perhaps even some trial and error, we can get something relatively useful out of this that can help us to predict the behavior of systems beyond what we can observe. So now we're back to so much for the theory. How do we apply this in practice? Well, we have TCP traffic, and we know that throughput is easy because it's just the queries per second, but figuring out the concurrency is a little bit harder. It's not particularly complex conceptually. We just have to keep track of how many things are running on the server at any point in time, and then slice it up into time windows and compute the average concurrency, the average number of things that were running during that time window per time interval. The pt-tcp-model tool knows how to do this. It makes it relatively easy for you. So let's do a visual model here of what happens. Some query arrives at t equals 0 and runs for 4 units of time. Let's call it 4 seconds. And then it completes, and that's the blue box, query 1. What if during that period of time a second query came in at t equals 3? This is the green box, query 2, and it completed sometime later. So we can count up the area under the curve, the total of Q1 and Q2, and divide by the length of the observation window, and we get the average concurrency there, which is just slightly greater than 1. So there was, during that time window, those 7 seconds, there was 1 query running all of the time, and briefly there were 2 queries running, so the concurrency was 2 for that brief little period in the middle. So pt-tcp model can do this. You just sort the output of the previous step. This request.txt, it's the same file that I showed you earlier. We just sort it by the first column, which is the arrival order of those packets. Remember I said that was going to be important later. And then we run the pt-tcp model tool again against this data with a command line option type equals request and save it to an output file. And it, by default here, when you run it in this mode, it slices it up in 1 second buckets. You can change that granularity, but by default it's 1 second. And now we have the concurrency and throughput measurements that we need, and we simply need a tool to help us do the regression. Spreadsheets generally won't cut it. You can do some nasty manipulations against the data and get it into a form that spreadsheets can work with, but it's really not elegant. Tools like GNU-plot and R are much better at this. They can do the regression against the data without transforming it into some other format. And again, we get these coefficients out of that. So I gathered, as I said, I think 8 samples and ran them through the tool and got a number of points, a number of measurements of throughput versus concurrency, or let me say that a different way, throughput at various concurrency levels. And I sliced this arbitrarily right down the middle. I said, let me take all of the points that have a concurrency of less than 4, and let's run the model against those. So those little green dots on the graph, those are the throughput versus concurrency measurements, and the red line is the universal scalability law fitted to this data. And I've printed a few other things on the graph here. I have a little set of scripts that I use to do this with GNU-plot. We can predict that the system is going to top out at 4,270 queries per second at concurrency of 9 queries running at once. And this sounds about right because this is an Amazon EC2 instance with only 8 CPUs, virtual CPUs. We shouldn't really expect to get anything more than 8 or 9 out of the system that has only 8 processors. That's just kind of a common sense gut feeling estimate. So this feels about right to me. A few of the other things on this graph are the sigma and kappa coefficients themselves and the R squared, which is an indication of how closely the points fit that line. In other words, how good quality the regression is. So what if I add in the rest of the data, the points, the measurements that I took at higher levels of concurrency? I've circled those here, and you can see they actually, they're falling off more quickly than we predicted. So we're not even going to achieve as much as this model predicted. And I'll come back to why that's interesting, useful, and not surprising a little bit later. Let me first say that we can also extend this technique to performance. I'm in the Oracle camp where performance is equivalent to response time. And there's a very good relationship between throughput, concurrency, and response time called Little's Law, which I mentioned earlier. And we can simply do a quick equation transform, and plotting the same data, we can actually model the response time of the system as well. And I've verified that this model actually matches reality. So here again, we have a good prediction of if we increase the concurrency on that system, what sort of response time increases can we expect? So again, just from the arrivals and departures on the system, I'm able to forecast how the system is going to scale as we increase the load beyond what we can observe. Now, the final thing is putting all of this together. I want to mention that you have to be very careful with this. You can easily get invalid results if you just capture some data and shove it into the model. You need to be careful. The first thing to do is always to plot it as a time series and make sure that you haven't captured the system behaving very badly in some unrepresentative kind of a way. For example, when the backup kicked off or something like that. You want to make sure that you're looking at a relatively uniform workload. I've tried this on many different systems and found good results on some and found completely meaningless results on some others that had a highly mixed or changing workload that basically it's pretty hard to predict what's going to happen with a system that has such inconsistent behavior. A couple of little notes: beware of dropped packets because that can confuse the analysis tools, and you might need to remove outliers. For example, if you capture 20 minutes worth of performance data, you might have some weird spots in there where something bad happened. Maybe somebody ran an ad hoc query and it caused things to go out of control for a little bit. Yeah, just snip that out. You'll be able to find those kinds of things. And removing outliers is a time-honored tradition with lots and lots of literature on when it's valid to do so and how to figure out whether something is an outlier or whether you're just irresponsibly cleansing the data by throwing out things that you don't like. There's a fine line between removing outliers and manipulating your data set. So you just want to be careful with all of those things. There are two cases where this scalability and performance analysis is useful, for a worst case and a best case bound. Now, for the worst case bound, I use this when I'm hunting for bottlenecks. Right? The worst case scalability of the system is what the universal scalability law actually models, when all of these workers that are on the system are always in communication with each other. Now, most systems ought to be designed a little bit more smartly than that, so that they don't have some quadratically degrading crosstalk between themselves. And in fact, if you want to design scalable systems, here's your recipe. Avoid seriality and avoid crosstalk, right? So most systems ought to scale better than that, and we can actually use this to determine whether we have behavior that doesn't match what we expect or a bottleneck in a system that ought to be investigated. And you can see this visually, but here's another caution. Be careful when you look at something and just kind of judge with your eye the shape of the graph. This graph doesn't have the shape that we expect because it's concave upwards, and that's because the x-axis is not linear, right? It's not even logarithmic. It doesn't even increase smoothly in powers of 2. We have some funny deviations in there. 4, 8, we miss 16, we drop in 24. So you just want to be careful about inspecting graphs visually and saying, well, that doesn't look like the universal scalability law. I think there's a bottleneck. You want to actually plot this against the scalability law itself and see how it shakes out. The other case is using this as a best case scenario. Now, if you drew some measurements on the whiteboard and held up a ruler and drew out the dotted line and said, I think looks like we have enough capacity to handle our anticipated Christmas shopping season load, you might be in real trouble if your system is actually going to scale like this. So we should expect that the system is going to scale worse than it's really supposed to. In other words, even though the universal scalability law is a worst case, we should expect that our systems are going to behave even worse than that. Right? So don't count on getting any more performance and scalability than the model will predict. And that's, again, why these points are lower than the red line here. Because, indeed, the system doesn't scale perfectly. It's worse than the universal scalability law predicts. And, in fact, if you look, those points are widely scattered there. And the system is so heavily loaded when it gets into these upper concurrencies that it's just behaving very badly and inconsistently. So you should expect that kind of thing. So as a summary, and I'll just breeze through this with my one remaining minute, we can get this very basic information from TCP, and we can find out things that you'll never find through other means, and we can forecast beyond what you can actually observe and measure for lots and lots of systems, not just MySQL, including ones that you don't have any internal counters or status variables or anything like that. And you can get really helpful insight into what the system is doing and how it might behave beyond the circumstances that you can observe. here's some resources that are good. Percona.com/software has the tools that I've demonstrated. And Neil Gunther's book, that's sort of the Bible for this kind of scalability modeling. And I've broken it down into something that I think is much more digestible for most people to read, the Forecasting MySQL Scalability White Paper. So that's all. If there are any questions, I think there have been no questions yet. I am happy to go ahead and email me. I'm delighted talking about this sort of thing. I'm a real scalability geek. And you can also follow me or message me on Twitter. Barry, do you want to?
Baron, thank you for today's presentation. We have one question.
Okay.
What if there are many queries in the one TCP stream?
I'm not quite sure how to interpret that question, if there are many queries in one TCP stream. I think the question might actually be asking something that I would phrase as, what if there's pipelining? So what if I send a query?
Baron, for clarification, says, for example, on Keep Alive HTTP.
Right, yeah, exactly. So Keep Alive or pipelining. So it's a much more complicated situation there and much harder to analyze, and that's an interesting area for me to dig into further, but I don't have any firm conclusions on that yet.
Okay, very good. We did have a question about availability of the presentation. Just to let everyone know, we have recorded today's presentation, and it will be available online. We'll send out an email with access information as soon as that is uploaded. Thank you for attending today's webinar, and we look forward to seeing you at future events. Thank you.
Thanks a lot, everyone. Bye-bye.
Bye.